Okay, so this is a continuation from what we talked about last time, and what we will end up learning how to do today, the objective, the focus, is so that we can graph these by hand without a calculator. Okay? Also, what we're going to learn today are the difference between a horizontal asymptote, a slant asymptote, and behavior asymptotes, and you will see what that all encompasses here in just a bit. But again, if you need to look over the video, rewind, fast forward whenever needed. Here we go. First step on all of these is to factor everything that you see. Can anyone tell me what the two factors will be in the numerator? X minus 6, x plus 4. Good. How about on the bottom? Yep, x minus 8, x plus 3. Now, we cannot reteach factoring every single week. It's something that you have to make a part of your knowledge to where you don't forget how to factor, okay? We're going to factor for the rest of the year. All right, undefined. Can anyone tell me when something is undefined? Yes, when the denominator is 0. So when I see something, a number, over 0, this is equal to undefined. How about if I have 0 over a number? That equals 0, okay? So, undefined is going to look at just the denominators, and what are those values? When are the denominator pieces equal to 0? 8 and negative 3. And you're going to say x equals 8 and negative 3. Guys, that's the only time that the graph does not exist. That means it exists everywhere else, so we're going to say negative infinity to negative 3, union negative 3 to 8, union 8 to infinity. The reason why these parentheses are there is because negative 3 and 8 do not exist. Yes?
Last time you said we just do x does not equal those.
Yes. Diego, you're absolutely right. You can, for the domain, also put x is not equal to 8 and negative 3, and it's just as much credit as what you wrote in interval notation. Cool? And guys, this shows that you're a little bit more of a beast because you understand that the domain is everything else except those things. Okay? All right. Removable discontinuity is the hole or holes in the graph. There could be more than one hole. Okay? How do I identify that from the factored piece? Anyway. Yep. Perfect. So when you have a 2 of a kind, like if this said x plus 3 and x plus 3, that would be the hole in the graph at negative 3. It's always the opposite. But the fact is, we don't have a 2 of a kind. Just like Lauren said, one has to be in the numerator, one has to be in the denominator to cancel out. So there will be no removable discontinuity for that one. Okay? Vertical asymptotes. Okay, after. You always need to do this removable discontinuity first before the VA and the HA, in my opinion. Okay? The VA is going to be the remaining scraps after you've accounted for the removable discontinuity. All the remaining scraps in the denominator are all VAs. They're all vertical asymptotes. They occur where? 8 and negative 3. And now we're going to put this as a vertical x is equal to 8 and x is equal to negative 3. So graph-wise, it would look something like this. Okay, so you have, these are vertical dashed lines. You could say at negative 3, whoops, I didn't get the dashed line. And the other one would be at, what is going on? Okay, my bad. So let me move this down. Oh my gosh. I'll just do these. Pretend like these are vertical, and this is going to be at negative 3 and at 8. Okay, and those are dashed.
What does that look like graphically? Like when you actually plot the graph?
I'll show you here in the problems that we did today, okay? Alright, so HA. The HA, you need to identify this In my opinion, the easiest place to identify it is not from the factored form, but from the original form. Because for horizontal asymptotes, you're going to use bigger on bottom, 0. Bigger on top, none. And then exponents are the same. It's going to be the ratio of the coefficients. Which one of these is this particular problem going to be? The what? Eats. It's going to be Eats ratio, because what exponents are the same, those two, the largest exponents are exactly the same. So that you look at the ratio of the coefficients, which is going to be 1 and 1. So y is equal to 1. And what that looks like is, at y is equal to 1, you have a horizontal asymptote. I'm just going to make this dash 2, just so you can kind of see. These are those vertical asymptotes. Alright, so let's keep going. We are now going to look at x and y intercepts. X's intercepts occur when y is equal to 0. Y intercepts occur when x is equal to 0. Okay? Here we go. So on this function, when y equals 0, that is when f of x is equal to 0. That means on a fraction, what piece is equal to 0? For the whole f of x to equal 0, what piece of this fraction needs to equal 0? The numerator. Nice. It's right there. Okay? So we're going to go back to the factored form. Again, the only place for the unfactored is the horizontal asymptote. Everything else is the factored form. What are the x-intercepts that you see? X equals 6 and negative 4. And yes, if you want to put 6, 0 and negative 4, 0, be my guest. It's just as correct. Okay? Y-intercept. This one, okay, so my mistake on saying the horizontal was the only place that you should do the original. The y-intercept also can be from the original. Because all I'm going to do is put in x is equal to 0 everywhere where I see an x. So I'm left with negative 24 over negative 24, which is going to be written here as what? Y equals 1, right? So y equals 1 or 0, 1. Let me reinforce. X-intercepts occur when the y is equal to 0. Y-intercepts occur when the x is equal to 0. Okay. So what I'm going to do is now I'm going to give you time in your groups, because remember you're competing for those points. I'm going to give you time. Alright, resuming the video. Real quick, step 1 is x squared minus 9. X minus 4, x minus 3. Further, we should identify that this is a difference of squares. Again, you need to be well versed with familiarity on this, because we can't go back over and over and reteach unit after unit. There's the factored form, and immediately I notice the removable discontinuity. So that occurs at x is equal to 3. Okay? Leftover scraps in the denominator are the VAs, which would be x is equal to 4. I can see it's undefined where the denominator is 0 at x is equal to 4 and 3. And the domain is everything except that, which you could have put negative infinity all the way to 3, 3 to 4, and 4 to infinity. Or the way Diego was saying, x is not equal to 4 and 3. It means everything else. The HA is from the original one, in my opinion, is the easiest way. And it's going to be exponents, botan. It's going to be bigger on top, because that 3 is bigger than 2. So the answer is none. N for none. There's no horizontal asymptote. And then we have x-intercepts. X-intercepts come from the remaining scraps. Okay, the remaining scraps. Again, this removable discontinuity hole in the graph, it cannot be a hole in the graph and then also be an x-intercept? It can't, because an x-intercept is defined. So the leftover scraps in the numerator are the ones that actually exist. Those are where the x-intercepts would occur, which would be at 0 and -3. And last but not least, the last one, we're just going to plug in x is equal to 0, which would 0 that, 0 that, 0 that. So I'd get 0 over 12, which is y is equal to 0. Okay? So resuming the video, let's move on now to why did we have this none right here for a horizontal asymptote is what we're going to discuss right here, right now. Okay, here we go. A linear, okay? A linear asymptote is x. A quadratic is x squared. A cubic is x cubed, and so on and so forth. You with me? All of these, whoops, all of these from quadratic down, they're called, listen, they're called in behavior asymptotes. Okay, that's what we're going to do here on this slide that shows in behavior. The slant asymptote is just this linear one right here of y is equal to x. Some kind of line is going to be this linear asymptote. Oblique, this is just a fancy way of saying that there's going to be no horizontal asymptote, but it'll be something else. Okay? And here we go. The linear asymptote that is not parallel to the x or y axis means this. It's a diagonal. It could be a diagonal going this way, or it can be a diagonal going downward. That's the line that the graph will approach as it goes to infinity or negative infinity, but not touch way on the ends. Okay? Here we go. Characteristics. The degree of the numerator is only one more than the degree of the denominator. So it's bigger on top by 1. Okay? So some examples that wouldn't include are this. Let's say we had x squared minus 4, and we had like x to the 4th minus 4. This is obviously not bigger on top.
Do you have one of these pages I can have?
Yes, in just a bit. X to the 4 minus 4 over x squared minus 4. This is obviously not an example because we want it to be just 1 degree, not 2. And it has to be on top. So this one was closer to actually being it, but it was more than 1 away. Okay? Alright. Alright, so resuming the video. Remember, it's bigger on top by 1 degree. So here is a perfect example because you see the bigger on top and it is by 1 degree. The non-examples are, of course, when it's bigger on bottom or if it's something other than just 1 degree. Questions? Okay, so let us continue. And look, this is what the graph would actually look like, okay? So at the bottom left down here, guys, the way you find a slant is to do long division. This is the only time it's going to pop up again. It's when you're doing things of this nature with rational functions. This is a subtraction. And here we go. I know it's been a little bit since we've done this, but again, for the rest of your math career, at least anything that you're going after this, you have to retain as much as you can because you can't relearn everything every unit. 3, 3, so we're going to start right here. We're going to ask ourselves, what times this first term gives us this? And what would y'all say? X. So you get x cubed minus x squared minus 2x. And remember that mistake a lot of people make. I'm subtracting all of that in parentheses. So the x cubed, watch this, I'm going to highlight them as I go. A positive x cubed minus this x cubed will be 0. a positive x cubed plus, because it's two negatives, you got to distribute this negative. Another x is going to be 2x squared. And then last but not least, it's a negative 3x. Two negatives make a positive. So it's negative 3 plus 2 is a negative x. Come down with this. Okay? Then you ask yourself, what next term would multiply with this x squared to give me that? And what do you say? 2. So it's a positive 2. You get 2x squared minus 2x minus 4. And you're going to have a remainder. When you subtract this, you're going to have a remainder. The 2's cancel, but you get a negative times a negative is a positive, so you're really adding 2 to this negative 1. So it'll be plus 2x. And then this negative and negative makes it a positive 4, which is going to be plus 3. This is your remainder, and just like you did way back in 3rd grade, you always put it over your original divisor. So the answer will be x plus 2 plus your remainder of 2x plus 3 out of x squared minus x minus 2. Now, this is the equation of this slanted line that is going to be dashed, okay? And the way we identify it is we are not going to graph this. We only graph this. That's the only thing. Okay? So over here, when you see this line, I'm going to make it to where you can see it dashed. And it should show up this time. I don't know why it didn't the last other times. But it should be the line that is going to be diagonal. And I don't know why it's not doing it. Oh well. I'll just do it like this. It's going to be right here. This is the line that it's talking about. Okay? This is x plus 2. Because look, you go up to 2, and you have a slope of up 1 over 1, up 1 over 1. And then you just draw the actual dashed line. So this right here is your slant asymptote. Okay? It's the line that the graph approaches but won't hit as you go to negative and positive infinity. The graph, if you put this into the calculator, is going to be all of this. It comes over here, and then it comes over here and goes out. What does the graph not show that you've learned from just notes that is important on this graph? Go ahead. All of this right here, this was just the original problem on the back. This one right here. Okay, but do you notice something that's not graphed, but that the shaded orange graph shows that there's some kind of pattern or something? Yeah. Vertical asymptotes. So there's probably one here, and there's probably one here. Okay? And we will talk more as we go through these notes today. Alright. In behavior. The biggest difference is this. Guys, it is still bottom. It's bigger on top. Therefore, there's no horizontal. There's no horizontal, but there can be a slant or a quadratic or a cubic. And in this case, they're cubic and up, or sorry, quadratic and up, because it's 2 or larger with a degree. Okay, so 2 or larger with a degree. And I'm talking about good examples could look something like f of x is equal to x cubed plus x squared plus 5 over x minus 6. Okay? Now looking at this, if I were to do in behavior asymptotes, these are other examples. Let's do this one that it gave us. Okay, let's do this example. We can do long division, but we can do a shortcut with this one. What is the shortcut to long division? Synthetic division. And the reason why we can do synthetic division is because the coefficient of x is 1. And also, this is just x plus a number or x minus a number. It's a linear with a coefficient of 1. Here we go.
Would it work with regular division?
It won't work with this one over here because this one was a trinomial. It only works with a binomial that's linear.
But this one will work with long division.
Yeah, it'll work with long division as well on this one, but that just takes too much. Here we go. So here we go. 1, -6, 7, and 7. And remember, we're going to put the solution here. So what number goes in the box if we're dividing by this? 3. So we copy, multiply, add. Multiply, add. Multiply, and we get a remainder of 1. So this right here is your remainder, and the way you're going to draw this is x squared minus 3x minus 2 plus 1 over my original divisor of x minus 3. This is your asymptote. But look, it's not a horizontal line. It's not even a diagonal line. This could be a quadratic asymptote. Okay, and I'm going to show you what that looks like here in just a bit. And I see what I just did there. This should be an x squared, okay? Right here, you can look on the right bottom. This is a non-example because these are only 1 away. Okay, that would be a slant asymptote. Okay, here we go. What does this graph right here look like? Let's check it out. Your asymptote is right here. And yes, it would have arrows going on forever. And the graph should have arrows going on forever. And yes, there is a spot here that there's a vertical asymptote that's not drawn yet, but that would exist. Okay, that's what we're developing today. Not only understanding what vertical asymptotes are, horizontal asymptotes, but also slant asymptotes, or a quadratic asymptote, and so on and so forth. Y'all with me? Okay. Let's move on to, okay, so on page 77, this is where you're going to put your homework. I will give you that here at the end of the class. And what I want to do now is go to the newer stuff. And we're going to do quickly a nearpod activity that'll help us learn how we're going to graph rational functions that look like this, and that look like this, and so on and so forth, all by hand. Ultimately, the goal is to do this, okay, by hand without a calculator, okay? So go ahead and log into your Chrome pads, tablets, and we're going to go to nearpod.com. Okay, so nearpod.com, when you get there, let me end this session that we're in right now. And guys, I want you, whenever you do this, you want to go to the very top and where it says like what's the code or enter a code, it's going to be like in blue letters. This is the code that you're going to use. Alright, resuming the video. We are learning how to graph rational functions by hand. No calculator. This is the ultimate goal. Alright, suppose a rational function. You cannot see anyone's names. I'm going to hide your names so you don't know who's who. Suppose a rational function has a horizontal asymptote at y is equal to 0 and a vertical asymptote at x is equal to -3 and x is equal to 2. What are some possible graphs that you could also draw? You see right here, they drew for us this graph that's shown in red. The only thing that they don't have that they should, in my opinion, is the horizontal asymptote at y is equal to 0. You with me? But the graph is here, here, and here, with arrows everywhere. What I want you to do is quickly on yours, I want you to draw 5 more graphs for me, just real quick, that follow the asymptotes, all different kind of combinations. Okay? And then we will discuss from what people have submitted here in just a bit. Resuming the video, I'm going to now pick some that have been submitted, and we're going to analyze which ones are good and which ones need a change, where and why. Is A good, yes or no? That looks good to me. It is following, these 2 arrows are following that. This is following that vertical asymptote. It's following the horizontal with that and that. And finally, it's hugging that vertical asymptote. That looks good. So A, I give it good. B, I say no. Why do I say no to B? It's not following any of these other asymptotes, but at the same time, it fails what? The vertical line test. It's not even a graph. It's not even a function. Okay? Was that yours? No worries. Let's go to, okay, this. You can't have those because, again, you need to hug these vertical asymptotes, these horizontal asymptotes. So I would have changed this to something like that. Change this bottom left piece to something like that, but don't go past it. It's almost like boundaries that you're trying to stay in. Okay? What's wrong with E? Fails the vertical line test. Let's keep going. A is a little hard to see, but I say A is good. I say B is good. C is good. The only thing that they were missing was this center one on that last one. Oh wait, no, that's my graph. That's my that's my graph. Okay, so let's keep going. Whoever that was really good. Okay, so what I will say is add arrows there, and it looks like your graph is doing like that. So just make sure that you keep going straight down and then go straight left, more rounded, and staying and hugging. What is wrong with these 2 pieces highlighted in orange? It never approached the horizontal asymptote. It never showed that it was going to hug y is equal to 0 forever. Neither did these. Okay? So I would say A, B, and just A and B are probably the good ones on this graph. Let's move on. This one looks really good. Whoever this is. Yep, good job. All of them work. Oh, cool. So what I would say is this is awesome because look, a lot of people have a misconception. They think, based off what we say verbally, that the graph should never cross the horizontal asymptote. That's wrong. It can cross the horizontal asymptote. It just can't cross it as you go to negative and positive infinity. Do you understand? So, can you cross the graph of y is equal to 0 here? You can cross the graph y is equal to 0. In other words, this line, this horizontal line of y is equal to 0, some people think, I can never go through that. But you can. Because the in behavior is what you're talking about. Okay? Here's a perfect example. A lot of people don't understand this, but I will show you right here. What if I said y is equal to 1 is your horizontal asymptote? Guys, you could have a graph that does this with oscillating waves. Is it crossing the horizontal asymptote? Yes, it is, everywhere. But if you go and you approach infinity, which actually should hurt your brain a little bit because you'll never reach it, over here is where you will not hit the horizontal asymptote. It's where you'll get super close at one point, and that's what it's talking about. That's why it's called the end behavior asymptote, because you're talking about positive and negative infinity that you'll never reach. Okay? So A is really good, but what is wrong with B? B, you need to show that you're hugging that horizontal asymptote. So I probably would have drawn these like this and like that. Okay, so we're just fixing it and then moving on. Let's keep going now. Alright, so what I want you to do, why is this graph not a rational function? We don't have time for it. This is where you type it in. We don't have time for it. Just verbally tell me, why is this not a rational function? Vertical line test. It is going to fail the vertical line test everywhere here and everywhere here as well, which means it won't be a function. Good. Let's go on to the next slide. Alright, so now I want you to draw this. Suppose a rational function has a vertical asymptote at x is equal to 1 and a slant at x is equal to this x plus 1, or x minus 1, sorry. I want you to draw, okay, so this is the graph that they drew. They drew this with arrows and this with arrows. What I want you to do is I want you to draw 3 other ones real quick, just like you did on the last one, of what are variations that could exist that follow the that follow the slant asymptote and the vertical asymptote. Resuming the video, let's see what you got. So let's go to this one right here. Oops, I gotta take mine off. So A is good, B is good, C is good. If there's any bad parts, I'm going to highlight them in orange if there are any bad parts, okay? That one looks good. Good. I think you guys got the hang of it fairly quickly. So the only thing that I'll say that looks kind of a little bit bad is this here. Why do you think I would say, and a little bit this one here, why do you think I say that those are bad? It's not hugging the asymptotes, okay? So I want you as close as you can get like that, and then the same over here like that. And then, of course, just like you've been doing, put arrows because you're talking about going to infinities. Okay, so let's see. Okay. Alright, so A is good. This is off. This is off. This is off. And this is off. Okay, and someone is saying they're struggling a little bit, which that person is struggling a little bit right now. Let's put this, the correct thing, in blue, okay? This right here, if you would have slid it down, that would have been acceptable. Because look, you are hugging this vertical asymptote and this slant. Okay, whoever it is, whoever you are. And then this one over here, the other one, would look probably like that. You could have put this one down here, but then you'd have to move this one over, otherwise you're going to fail that vertical line test, and that would be a good graph right there. Okay? Alright. Let's look at, those look good. Those look good. Oh, okay. So C and B are wrong. What are they wrong? How are they wrong? B and C are wrong. How are they wrong? There's only one graph. It's half the graph. This VA right here is saying that's the only time that you are going to not have something defined. Everywhere else, there needs to be something there. So you could have this over here, or you could have it on the bottom. Okay? And then you could have this over here. Let's say that you even had a removable discontinuity. You could have something like that. Okay? Many variations. Alright, so let's move on. Let's go on to, there's a quiz. I want you to answer those 5 questions real quick and see how you do. Oh, resuming the video. We gotta unfreeze. Alright. Correct, incorrect. I think with this, I'm not able to see it, but it's all good. I just want you to get a little feedback as far as that goes with those graphs. What we're going to do now is we're going to learn how to sketch this by hand. Okay, but I want to go back to our notes to do this. Okay, so let's go to page 70. I believe it was 77 was where you're going to put your homework in there. You can staple that if you want. And now we're going to go to page 78, I believe. Okay? So day 4, page 78. Here we go. This is page 78. So this is next. After your homework page, this is what's next. Alright. Guys, this is where it starts. We are going to do this by doing it by hand and figuring out what pieces go where, okay? If this is my equation that's given to me, what is the first thing that I should do? Anybody? Factor. So GCF, you get x squared minus 9, and then you get x minus 1, or sorry, x plus 1 and x plus 1. Okay. Furthermore, it's not factored completely until everything's down to x. You know what I mean? Linear. This is still quadratic. We need to break this down. And what would x squared minus 9 break down to? Nice, nice. So x plus 3 and x minus 3 is what this is going to break down to, because it was a difference of squares. And again, I can't stress it enough, guys. You can't forget the skills you've learned, because you're going to be using them for the rest of the year. All right. The horizontal asymptote, you tell me. Factored form or the original, which one should I use? The original. Okay? So, blah, blah, blah needs ratio with this original. You tell me, what's my horizontal asymptote going to be? Y equals 2. Thank you for the y. Y is equal to 2. Because it's each ratio. You're right. Exponents are the same. So it's the ratio of the coefficients. 2 over 1. Alright. Removable discontinuity or the whole. Do you see one? Yes or no? No. Because you need a 2 of a kind, right? One has to be in the numerator, one has to be in the denominator. So there will be none. A lot of rules to remember, but I promise you it's very repetitive when you learn them. It almost feels like when you learned how to do quadratic formula way back in the day, it seemed like a lot of work just to get those answers, but no matter what, you'll get those answers. Alright, X-Intercepts. X equals what? I can't hear you, but not negative 18. Negative 3 and positive 3. Because remember, the X-intercepts come from the numerator is equal to 0. Taking away all the leftovers, or it's just the leftover scraps. Taking away all the holes in the graph. Since there were no holes in the graph, it's just going to be at x is equal to negative 3 and positive 3. Okay? Vertical asymptotes. Where are those at? X equals negative 1. Because vertical asymptotes are all the scraps in the denominator, again, that are not already a removable discontinuity. If it's a hole in the graph, it can't be a hole and a VA. Alright. So let's draw what we know so far. We know our VAs occur, or our VA occurs at x is equal to negative 1. So I'm going to go ahead and draw that right here, okay? Furthermore, we know we do not have, we don't have a hole in the graph, but we do have a horizontal asymptote at y is equal to 2. X-intercepts, we have them at negative 3 and positive 3. And now comes the last part of knowing how to graph these things by hand. And you'll need to know this information, especially if you plan to go to calculus, how to do these by hand. Okay? Let's look at a number line. This is a signs test. You're going to see where's it positive, where's it negative. That's it. Okay? But you have to identify all the numbers that are important to see. Okay? So how do you identify all the numbers that are important? You're basically going to say everywhere where the top was 0 and where the bottom was 0. You with me? So, at -3, at +3, and at -1. Those are all of my zeros of the top and the bottom. How many intervals does it look like we're going to test from what you see right now? 4. 1, 2, 3, 4. Now here we go. What number should we test in the first interval? What could we throw in there? -4. What could we throw in the second interval? -2. How about the third? 0, which is the easiest one for that one. And the last one? You could throw in a 4. And where are you going to throw these values in? You're not going to throw them in the original. You're going to throw them in the factored form right here. Everywhere where you see an X. Your number sense has to be on point. Okay, you're not going to be able to have a calculator go. You've got to be able to do this in your head. Let me show you what you're looking for. If I put in this -4 to test it out, everywhere where you see these green X's, -4 plus 3 is a negative. -4 minus 3 is a negative. I don't care about this 2. I don't. I just care about the signs of each piece, okay? Because this 2 is positive, I just can say that it's positive, and it'll be positive all the time. Now, if I put this -4 over here on the bottom left, -4 plus 1 is a negative. -4 plus 1 is a negative. Guys, what would this be as an entire multiplicative quotient? Positive or negative? Be positive. Because positives, if they come in pairs, become negatives. Or sorry, I said that backwards. Negatives, if they come in pairs, they become positives. So the whole product will be positive. Okay? Let's plug in -2. Okay? So it's still +2 here. Now I'm going to plug in a -2. -2 plus 3, positive. -2 minus 3, negative. -2 plus 1, negative. And -2 plus another one is negative. Guys, what does all that give me? A negative. Now let's plug in 0. I know it's positive for this 2. That will always be positive. You tell me, what are these other ones? What are the other top 2 going to be? Positive and negative. How about the bottom 2? Positive and positive. So what is all of this? Negative. Right? And then at the last, if I plugged in 4, and you would have put it in everywhere there's a green X, what do you think it's all going to be? Positive. So look, this is what this means, guys. Negatives mean that they're not below the horizontal asymptote. That's what a lot of people mistakenly do. It doesn't mean below the horizontal asymptote. It means below the x-axis. That's what negatives mean. Okay? Positives, okay, these positives are going to mean it's when it's above the x-axis. Again, the common mistake people think is they think it's above the horizontal asymptote. No, it's above the x-axis. So I need to be above the x-axis for this first one, hugging the horizontal asymptote. And that's what I've drawn. Okay? Now I need to be below the x-axis, hugging the vertical asymptote. You see how I'm doing this? Then I need to be below the x-axis, hugging, coming from that vertical asymptote. Notice how I went to that x-intercepts of -3 and 3. And then for the last piece, I need to be above the x-axis, approaching my horizontal asymptote. But I promise, it's a lot, but it's the same thing over and over and over again. Sign test, VA, so on and so forth. All right, ultimately, this is what we're doing. This is the culmination, guys, of this unit, what I'm about to show you right here, okay? This is an intro into calculus. Here we go. This means f of x, right here, is the graph that we drew, Okay, and I'm not going to make it that ugly. I just want to visually show you what that's talking about. So if the graph is f of x, and I asked you, I want you to approach as x approaches negative infinity. This, what I highlighted in blue, it means this. As you go to negative infinity, okay, what is the graph going to? You know what I mean? If you were to jump on the graph and go to negative infinity, what does the y value of that graph want to be? It wants to be what? Y equals 2. Let me show you. I will do it with this dot right here. So look, right here, I'm going to approach negative infinity. But I can only do that, actually let me do it with this one so it's a little bit more visible. Whoops. I'm going to go to negative infinity, but I'm going to have to do it by jumping on the graph. And I'm going to negative infinity at the same time. What is the y value that it's trying to hit? It's trying to hit what? 2. And the way you're going to describe this, as x approaches negative infinity, f of x, otherwise aka the graph, is approaching 2. To me, I think these are the culmination kind of problems with this rational functions that you definitely will expect to see on your final exam. Okay, right before winter break. Now, let's approach positive infinity. Looking at the graph, okay, if I approach positive infinity, if I jump on the graph, again, I'm approaching positive infinity, going to the right. What will this approach? Still 2. So you're going to say as x approaches positive infinity, f of x is approaching 2. Be careful with the next one, okay? This one's a little bit trippy. Here we go. I want you to now visualize, and I'm going to help you out before you see it. The notation that you see here is that as x approaches negative 2, okay, and this little negative right here after the 2, it means from the left. So if you approach negative 2 from the left, it's saying you're doing this. You're approaching negative 2 from the left. Okay, and if you approach negative 2 from the left, that means ultimately you're going to hit right here. But again, you have to jump on the graph to do this. Okay, so this one's not as easy, but you're approaching negative 2 from the left. Let's jump on the graph, approaching negative 2 from the left. What is that number that you would hit? Negative, not negative 1, you're close. Negative 2. Okay, because that right there is negative 2. Okay, so we're going to put, as x approaches negative 2 from the left, f of x, oops, f of x will approach negative 2. Now, notice the notation for this last one. As you approach negative 2 from the right, positive means from the right. Okay, it's going to look like this. On the graph, let's go ahead and jump on the graph. And we're going to approach negative 2 from the right. So we're going to approach right, boom, right there. But we got to jump on the graph. Here we go. So I'm approaching, and then it disappears. And then comes out of a wormhole, and then it's still approaching, and right before it gets to negative 2, what's f of x approaching? Right before it hits, just before it hits x equals negative 2, where is it going to be hitting y-wise on the graph? Negative 2 again. This one right here is where it's hitting. And you would ultimately say this. As x is approaching negative 2 from the right, f of x will approach negative 2 still. We're going to get more practice with these limits too, by the way. And I don't expect you just to get it with 2 problems. Woo! Good stuff. Alright, let's do some practice. So homework worksheet. Again, this is due next class. That'll be for page 77. What I want to do is, I want to look at these with you together real quick, okay? Notice the graph. And then this will be it. This is it. After this, then you're pretty much set for your homework. I think you're good to go to get your homework established. Alright. If I am looking at f of x, which is the graph that you see over here in blue, okay? So let me highlight that with blue. And I told you, I want you to approach, okay, that's what this arrow means. It means to approach. I want you to approach negative infinity. What would the y value be if you're approaching negative infinity? In other words, as x goes to the left, what would the y hit? What would the graph go to? Negative 2. Good. Because the graph is going to do this. It's going to keep going and it's going to hug that horizontal asymptote, which wants to be negative 2. We're not saying what it is. We're saying what it wants to be. Okay? And that's what a limit is all about. Okay. So you'll say negative 2. How about if I go to positive infinity? Okay, so now I'm going to go this way. What does the graph want to be? Still negative 2. Now you're starting to get the hang of it faster. Okay? Let's say that I want to approach negative 2 from the what? From the left. So now I'm going to approach, let me erase this a little bit so that I don't confuse you. I'm going to approach on the graph negative 2 from the left. Alright, so approaching negative 2 from the left, what does the graph want to approach? Not negative 2. Okay, I see what you're saying. Think of a y value. Okay, the other we're giving these answers right here are y value answers. They're numbers that are given on the y-axis. You see, you guys said previously the negative 2 because it made sense. But now, the graph, what will it approach? Negative infinity. How about if I approach negative 2 from the right? Again, I'm going to approach negative 2 from the right. Got to jump on the graph. What will the graph approach? A positive infinity. It's going up here as you approach negative 2, as you approach negative 2 from the right. Do you understand it, guys? Questions before I stop the video? Nice job. Nice job today.